In this video, we are going to talk about systems of nonlinear equations. I want you to take a shot. What do I mean when I say a system of nonlinear equations? How is that different than a system of linear equations? Yeah, literally in the name. A system of nonlinear equations is going to have at least one equation that's not the equation of a line. That could be the equation of a parabola, kind of like we see in this example here. Wow, very bad at tracing that. Or a circle, or an ellipse, or literally any other function besides a line. And we've actually seen those before, right? In Unit 1 at the beginning of this class, we talked about different parent functions. Like as you see here, we have an absolute value function and a parabola that are a part of this system. And we can see them graphed here. Now, I mentioned this a little bit. We didn't go into a lot of detail on it when we talked about systems of linear equations. But whenever we are given the graph of a system, how did I suggest that we find our solution? What are we looking for on the graph? Yeah, we're looking for points of intersection. And the key thing that will come into play a little bit later on is that it is points of intersection with all parts, all functions that are part of the system. In this case, we only have two functions, so we're looking for just literally any points of intersection, and we see one here as well as here. Because we know when we graph these functions, those are nice coordinate points, and our solutions are going to be at the point 1, 0, as well as the point 2, 1. Let's go ahead and take a look at one more example. Again, we see another absolute value equation in addition to a square root function. And we see that there is only one solution, one point of intersection between these two functions at a point 1, 0. Totally fine that we only have one solution, one point of intersection. Let's say we have an example like we see here. What problem would we have with solving the following system? We can see the graph here. We would know how to graph these by hand. I'm looking at my point of intersection. What problem will we have with trying to come up with our exact solution? As you're trying to find the solution to this system, you would realize that it is not at a nice coordinate point. We're looking, it's somewhere in the middle of an x value of 0 and 1, a y value between 1 and 2. Like, we would have to estimate. We have no idea what the exact value of that is if we were just looking at the graph. And so that's going to lead us into the bulk of our notes for today, and that is methods for solving nonlinear systems algebraically. And this is going to be similar to the methods we use for solving systems of linear equations, such as substitution and elimination. But of course, it's going to take a little bit more math on our part in order to do this algebraically and find these solutions. And just like let's go ahead and start with substitution. And just like we did with substitution in solving linear systems, we are going to want to use substitution and be like pushed to use substitution to solve whenever we have one equation that is either like x equals or y equals some variable equals stuff. And in this case, x equals y plus 1, we are going to plug in y plus 1 in for x and substitute it there. So that I have what you see here for my first line of work in green. Now when I were like to multiply all of this out, I would end up being left with a quadratic, and in order to solve for y, to solve a quadratic, we know we need to set everything equal to 0 so that we can factor, and then solve for y. We've been multiplying binomials with other binomials for really the whole trimester. And so I'm going to go ahead and do that for us already. Y plus 1 squared, we cannot forget the middle term, plus 2y. And from here I can combine like terms, move everything over to the other side. So I'm going to subtract 5y from both sides. So I'm left with 0 equals y squared minus 3y. And then plus 1 minus 1, that cancels out. And this is all I'm left with. I'm going to go ahead and have you factor this and tell me what you get for y. Nice. In order to factor, I need to pull out a GCF, set each of these factors equal to 0, and solve for y. So I get y equals 0 and y equals 3. And that would be our first step of solving this system, once I substitute, is to find y. Now, I'm going to go ahead and plug y into my system in order to find x, just like we've been doing before. But this is going to look a little bit different because obviously what we notice is that we actually have two values for y. And we need to make sure that we're plugging both of those in because both of those will give us different points where our functions intersect, different solutions. And so our second goal is to find x, and we will do that by plugging y in. I'm going to go ahead and use our second equation, x equals y plus 1, because it's already set equal to x, right? Not much moving around I'll have to do. And the key here is that I am plugging in both values for y. What I like to do is draw two arrows and put whatever y value I'm plugging in for like that equation, just to help me like organize my work and really understand, hey, like what am I doing here? I'm doing x equals, well, I'm plugging in 0 for y, so x equals 0 plus 1. And then over here to the right, I'm plugging in 3 for y, so x equals 3 plus 1. When I do this, I get an x value of 1 and an x value of 4. Now the last thing we need to do, of course, is write our solutions, and those are points of intersection. Those are points on our graph, and so our solutions need to be in the form of points. Do not lose track of which x value goes with which y value. Again, that is why I really like organizing my work in this way. I very clearly can see that this x value of 1 is going with my y value of 0. So that's going to be my first solution. 1, 0. You tell me my second solution. Yeah, I get a solution of 4, 3. And if I were to graph these two functions on Desmos and look at those points of intersection, I see 1, 0 and 4, 3. Looks like we did some pretty good math there. All right, let's go ahead and try using elimination to solve a system of nonlinear equations. If I'm deciding to use elimination to solve this system, one thing that I notice right off the bat is that my y squareds, one is positive, one is negative. So as long as the coefficients out front of those two terms are good to go, then those are going to cancel out when I combine these equations, when I add them together. The other thing I like about my y squared terms is that compared to my x squared terms, 2 and 3, smaller numbers than 3 and 4. And so like if I were to multiply this top equation by 3 and my second equation by 2, those numbers that I'm multiplying are going to be a little bit smaller, a little bit easier to do. And so I'm going to go ahead and first try and cancel out or eliminate my y squared terms. I do all my multiplying, get my new equation set up here. Let's go ahead and add them together. So I get 17x squared. My y squared terms cancel out, so that is equal to 99 plus 54, that's going to be 153. Next, of course, divide both sides by 17 so that I get x squared to be equal to, not going to lie, definitely needed to use a calculator there. So 153 divided by 17 is 9. In order to get x equals, I'm going to take the square root of both sides, so I get x equals, what do I always need when I take the square root myself? Yeah, plus or minus 3. I need my plus minus. All right, so I have my x values. That was like my step 1, solve for x. Now I get to solve for y. Again, it doesn't really matter what equation I'm plugging y into. I went ahead and chose the first equation just because this y squared term is already positive, and that's what I'm looking for. And so I'm going to plug in x equals 3. I'm also going to plug in x equals -3 to get my two different solutions here. At least as far as I know, two different solutions. Now let's go ahead and do it. You do it on your own and then check with my work here in a second to see how you did. Okay, let's take a look at my work for a second. Of course, I'm plugging in 3 for x on the left side. I'm plugging in -3 for x on the right side of my work. And hopefully near the beginning you realize solving for y in these equations was going to be the exact same because we're squaring 3 and negative 3. And so I only did the work on the left side, and when I got y equals plus or minus the square root of 3, I knew that was going to be the exact same when I plugged in negative 3 for x on the right side of my work. And so, knowing that y is plus or minus negative 3 when I plug in positive 3 for x, I got the solution that you see here that I've boxed. 3 comma plus or minus the square root of 3. And the same thing for when I plug in x equals negative 3. Negative 3 comma plus or minus the square root of 3. Now I'm curious, can you tell me how many solutions or points of intersection does this system have? This system actually has 4 solutions. And I've written in black beneath each solution that we had already come up with. I wrote out each individual point, right? This plus or minus 3 comma plus or minus the square root of 3. That's like saying, hey, the point 3 comma positive square root of 3 in addition to the point 3 comma negative square root of 3. Same thing here over here on the right. And when we graph these two equations that are in this system, we can see each of these 4 points of intersection, each of these 4 solutions. Sweet. Let's do like 1 or 2 more examples together, and then we'll go into some individual practice. Let's scroll on down. All right, let's read this problem together. If x comma y is a solution to this system of equations, what's one possible value of the product of x and y? Ooh, okay, so we're looking to find our solution and then multiply x and y together. That's what product means. I'm curious, when you're looking at this system, these two equations, how do you think you would solve this? I don't know about you, but when I see y equals and y equals, I just want to set those babies equal to each other. And so in this case, you see that I have done that already, and my goal is to now solve for x. This is a quadratic. We know how to solve quadratics. Let's go ahead and start by just solving for x. When I solve for x, I end up getting 2 values for x, positive 2 and negative 1, that I'm going to plug into one of the equations in my system. The math in the second equation, y equals negative x plus 3, looks a little bit easier, so I'm going to go ahead and plug these values in for x into this equation. So x equals 2 and x equals negative 1. Go ahead and do it for me. And yeah, you know what? Go ahead and answer the question. Come up with our solutions and the ultimate response to the question, a possible product of x and y. All right, when I plug in both of these values for x and solve for my y's, I come up with 2 solutions at 2 comma 1 and negative 1 comma 4. And when I multiply x times y for both of those solutions together, I have a possible product of positive 2 or a possible product of negative 4. Let's take a look at one more example. I'm going to have you do most of this on your own, but I'll go ahead and help us get started. We are trying to think about solving for, either x or for y. One thing that's going to be a little tricky and something that could potentially trick you up, I know it tricked me up back in the day. You might say, hey, I noticed that my y terms, one is positive, one is negative. They both have a coefficient of 1. Like, let's add these equations together and cancel out our y's and get going. But you can't do that here. In our first equation, we just have negative y. In our second equation, we have positive y squared. That squared changes things for us. And so that kind of forces us into having to cancel out our x squareds first. And so I'm going to go ahead and multiply this first equation by negative 1 to change the sign, so that when I rewrite it, I'm left with negative x squared plus y equals negative 5. And so that now when I combine these equations, my x squared terms cancel out. I'm left with y squared plus y. I cannot combine those because they are not like terms, so I need them to both be here. Y squared plus y equals 25 minus 5. That would be 20. All right, from here, you guys can get to it. Solve for y. Plug that value or those values into an equation to solve for x, and then come up with our solutions. We'll check back here once you are finished. All right, when I solve this system of equations, I get, 3 solutions, 0, -5, positive 3, 4, and negative 3, 4. All right, let's get to some practice.